Okay, so till now, what we have been discussing is about NMOS transistors or N-channel MOSFETs. So you already know what is the structure of the N-channel MOSFET looks like, but in today's lecture, we'll look a little bit into PMOS transistors as well, and what are the differences of PMOS transistors with NMOS transistors, and how do you actually analyze PMOS-based transistor, or if you see a PMOS-based circuit. Along with that, we'll see something called a current meter that can actually meter a specific amount of current from one part of the circuit to another part. And we'll see that how this will be useful in our later lectures. And once we're done with that, I'll provide you a cheat sheet for MOSFET-based amplifiers. So if you have understood all the different details about NMOS transistors, PMOS transistors, and so on, and all the different amplifier structures that we have studied in the class so far, all you'll need is this cheat sheet to look into so that you have everything at the same place. So I'll also go over the cheat sheet a little bit, but before doing that, we'll be looking into the PMOS transistors a little bit. Okay, so this is something we were discussing in the previous lecture, that of course there is an effect of finite transistor output resistance. And if you go back to this particular, so for example, when you look into common source amplifier, the way we represented the model of the transistor is that you have an open at the input side. So that gives you your VGS. You have a GM-VGS, which is your current source, which is part of the MOSFET small signal model. And then we directly said that, okay, whatever load resistance we are connecting at the drain, that comes in parallel with that GM-VGS current source. But in reality, that transistor will have a non-ideality that, okay, there could be a parallel current source, that could be a parallel resistance to this current source. And this is part of the transistor model. So this GM-VGS, that amount of current in parallel with RO, that is your transistor model. So in many cases, we ignore the RO. We might say that the RO is infinite for the transistor. And then what will happen is that whatever RB you put at the gain, eventually your gain will be determined by GM times RD, or GM is given by the transconductance of the device times RD. But if you want to be a little bit stricter with the equations that you use, so instead of this gain being minus GM times RD, what you will have is minus GM times RO in parallel with RD. So that becomes the effect of your output resistance, or RO, for the transistor when you have this kind of a common source configuration. We have also seen that depending on the value of that RO, the value of this output resistance is basically 1 upon lambda ID. And that comes in from the fact that, okay, your equation for ID is K over 2 VGS minus VT whole squared times 1 plus lambda times VDS. Of course, to find out RO, you have to consider that you have a finite amount of lambda. If your lambda is 0, your RO becomes infinite, and that's the ideal scenario. And remember the ID versus VDS characteristics. So if you're plotting the VDS of the MOSFET in the x-axis and ID, or the drain current of the MOSFET, in the y-axis, your ID versus VDS characteristics ideally should have looked like this. That ID should saturate and become exactly parallel with the VDS axis. But instead, you'll see that there is a slope, right? So ID will keep on increasing with VDS because of this 1 plus lambda VDS factor. And 1 upon that slope, 1 upon the slope of the ID versus VDS characteristic is basically your RO, right? The output resistance. Because what is resistance? Resistance is del VDS over del ID. Remember that VDS and ID both are output quantities. The VDS is your output drain to source voltage of the MOSFET, and ID is the output current of the MOSFET. So del VDS over del ID will definitely give you the output resistance, just from Ohm's law. Resistance is voltage divided by current. So if you take that into consideration, so RO is basically del VDS over del ID, whereas the slope of this ID versus VDS characteristics, so if you take this slope in the saturation region, what is that slope? That slope is del ID over del VDS, right? So that's why I said that the 1 upon the slope of your ID versus VDS characteristic in your saturation region gives you your RO, or the output resistance. Now you can find that out from the equations as well. You have already found out what is the equation for GM. GM is basically del ID over del VGS, or derivative of your ID equation with respect to the input voltage. So output current divided by input voltage, that gives you transconductance. And you have already found out multiple forms of that GM equation. One is K times VOV, the other one is square root of twice K times ID, and the third form is twice ID divided by VOV. Depending on what quantities are provided to you, you can use any of these three equations for your GM. On the other hand, GO, or the output conductance, is del ID over del VDS, or the derivative of your ID current with respect to VDS. And that you can find out as lambda times ID just by doing this derivative of the ID equation that were given to you before. So GO, or the output conductance, sometimes it's represented as GD, or the drain conductance, or GDS, or the drain to source conductance. And all of them represent the same thing at the output. Now RO is basically 1 upon GO. So your RO will become 1 upon lambda ID. And that's basically 1 upon the slope of your ID versus VDS characteristics. So definitely, if you have a finite RO of the transistor, you are actually taking care of or taking into consideration this lambda, or the channel length modulation parameter, which means that the ID versus VDS does not actually saturate in the saturation region. There would be a slope, there would be a finite slope, and because of that, you'll have a finite RO. And the value of RO will be 1 upon lambda ID. Now, what does that mean? That means that if you consider just the MOSFET, if you just considering the MOSFET, you have this GM-VDS current, and you have this RO resistance at the output. That itself gives you a gain of minus GM times RO for the common source configuration. Okay? So sometimes GM times RO is called the intrinsic gain of the MOSFET, because again, transconductance times resistance is basically a voltage gain, because transconductance is current divided by voltage. Current divided by voltage multiplied with the resistance becomes voltage divided by voltage. So voltage at output divided by voltage at input. We have solved this multiple times, and we have shown that transconductance multiplied with output resistance actually gives you the voltage gain. Again, if you want, I can write that down. GM times RO is basically your small signal AC output voltage divided by, or let me write it as small signal AC output current divided by small signal AC input voltage. Right? That's the definition of your GM. I can write it as del IO divided by del VN or del VGS, but in this case, I'm just writing it as small signal. So the small signal parameters represent the same thing. Now that multiplied with RO actually gives you VO divided by VN. Right? And that's why I say that any transconductance multiplied with output resistance gives you the voltage gain. That becomes V out divided by Vin. Because at the output side, your current, output current multiplied with output resistance gives you output voltage. Again, Ohm's law. Okay. So this is something that we already know, but what this means is that for the MOSFET, you will have an intrinsic gain parameter, that GM times RO, that gives you an intrinsic gain for the MOSFET. And the value of GM times RO, you can again find it out. GM you can represent as twice ID divided by VOV, and for RO you can represent it as 1 over lambda ID. So ID and ID gets cancelled out. What you have is 2 divided by lambda times VOV. That's your intrinsic gain of the MOSFET, and you can never get a gain which is higher than this. Why? Because GM times RO, we are defining it as the intrinsic gain of the MOSFET. As you put resistance at the drain, what you will have is basically, like if you just take the absolute value of it, it's GM times RO in parallel with RD. Now RO in parallel with RD will always be less than equal to RO. Right? So if you are using a small RD, RO in parallel with RD will become just RD. If you are using a very, very large RD, RO in parallel with RD will become RO. Correct? So maybe if I just write that down, RO in parallel with RD will be equal to RD when RD is much smaller than RO. So if the resistance that you're using at the output side at the drain node is much smaller than the RO resistance, which is usually the case. In that case, your RO in parallel with RD becomes RD, and that's why we say that the gain of the transistor is GM times RD. But in the scenario when your RD is much larger than RO, let's say you have a giga ohm resistance or something like that. Let's say if you have a giga ohm resistance and that's something you're connecting at the drain side, then that would be larger than your RO. And usually the RO of the transistor is in the range of hundreds of kilo ohms. So in that case, your RO in parallel with RD will be RO. So your GM times, if you're plotting your GM times RO in parallel with RD in the y-axis, and if you're plotting, let's say, the value of RD in the x-axis, then you'll see that for small values of RD, your gain of the transistor will be GM times RD. And for very large values of the resistance RD, your gain of the transistor will be GM times RO. Right? So this saturation represents GM times RO for the gain of the transistor. So here in the y-axis, we are plotting the gain of the common source stage, and that is GM times RO parallel with RD. And in x-axis, we are plotting the RD resistance. So for smaller RDs, you have GM times RD. For larger RD, you will have GM times RO as the gain of the system. Okay. So that's just a recap of what we are discussing in the last class and the effect of the RO or the output resistance of the transistor. Today we'll take a look at PMOS transistors as well a little bit, and we have already looked into the different symbols of the p-channel MOSFETs. So this is how the different symbols of the p-channel MOSFET is represented, and as we had said earlier, that the two symbols that we'll primarily be looking at is this one, which is the prevalent symbol you'll see for p-channel MOSFETs in analog circuit books. And in digital circuit books, you'll see this symbol, that the NMOS is represented just as this transistor without any arrow, but as the PMOS will be represented with a bubble or this inversion at the gate. So which just means that the PMOS is a dual of your NMOS transistor, or it's just an inverted version of your NMOS transistor. If you use the other symbol, which I have represented here, what you generally do is that you represent this arrow at the source terminal of the transistor. Now, remember, for NMOS, the current flows from drain to source because electrons flow from source to drain. For PMOS transistors, holes flow from source to drain, which means the current will also flow from source to drain. So that's why the current comes into the source terminal and goes out of the drain terminal for the PMOS. For NMOS, current comes into the drain terminal and goes out of the source terminal. So that's just a way we represent the PMOS and NMOS transistors in terms of their symbols. But now in terms of the equations, if you know the equations for NMOS, you can write down the equations for PMOS very easily. Because again, remember that PMOS is just a dual of your NMOS transistor. So what you generally do is that you can represent it with the same equation. So for example, ID was K/2 VGS minus VT whole square for your NMOS. For your PMOS, it will be minus K/2 VGS minus VT whole square. Why is the minus coming in? Because again, for the PMOS and the NMOS, the current flows in different directions with respect to the source and drain. For PMOS, the current comes into the source. For NMOS, the current goes out of the source. And that's why this negative sign comes in. But if the negative sign confuses you, which I get confused a lot of times, so the way I try to think about these equations is that instead of writing VGS, so for example, for NMOS, you know that you need to have VGS greater than the threshold voltage, right? For PMOS, what you do is that instead of writing VGS, you write VSG. right? Because everything is reversed for PMOS. For NMOS, for your NMOS, the current flows from drain to source. Right? This is the direction the current flows for an NMOS transistor. For a PMOS transistor, the current flows from source to drain. So this is for NMOS and this is for PMOS. For PMOS, the current flows from source to drain. And you already know as an electrical engineer that the current always flows from a higher voltage or a higher potential to a lower potential. Right? So which means that for the NMOS transistor, the drain is at a higher potential and the source is at a lower potential. And you already can understand that this is true because the circuits that you have learned, you have mostly grounded the source. So think about your common source amplifier. You have grounded the source, which means the source is at the minimum potential in the circuit. So drain is at a higher potential, source is at a lower potential for NMOS, whereas for PMOS, the source will be at a higher potential and the drain will be at a lower potential. Usually you connect the source at the highest potential of your circuit, that is your VDD. And again, why do you do that? Because think about the internal structure of the PMOS. So you have a P-type source, you have a P-type drain, you have a gate and the gate oxide on top. So this is the gate and this is the oxide layer. And then you'll try to form a channel between the source and the drain, right? You'll try to form a channel by applying a negative voltage at the gate. So you'll apply a negative voltage at the gate. And why do you want a negative voltage at the gate? Because you want to attract holes into the channel region. Remember that P-type semiconductor has abundance of holes. Again, this P-type semiconductor has abundance of holes. But in between, you have an N-type semiconductor, which has abundance of electrons. So you want to invert that. You want to create a channel, and you want to create a channel by attracting more holes. So the positively charged carriers from the bulk region. So you want to attract them to the channel. You also want to attract some of the positively charged carriers that are present in the P-type region, and you want to attract them into the channel. And to attract positively charged carriers, what do you need to apply at the gate? You need to apply a negative voltage, right? So that's what the basic structure of the PMOS looks like. Now remember that what do you need to do with the as you're basically looking at the PMOS structure, what do you need to do with the body or the bulk? For NMOS, you know that you have to connect the bulk terminal to ground so that the PN junction diodes are reverse biased. They do not become forward biased, because if the PN junction diodes become forward biased, there would be a current flow between the diode, which you don't want. So again, the same concept applies here, that this PN junction diode has to remain reverse biased. And for the PN junction diode to remain reverse biased, you have to apply a positive voltage at the N-type semiconductor, right? So you want to reverse bias the PN junction diode, so you need to apply a higher voltage at the N-type semiconductor. So generally you connect your VDD to the bulk of the PMOS. So usually the bulk of the PMOS is connected to VDD, and also the source of the PMOS is connected to VDD. So that this junction, the PN junction, is not forward biased. Also, this other PN junction is not forward biased because N-type, the bulk, is already connected to the highest voltage, which is the VDD. And if you do that, then what you need to have is basically a negative VGS, a negative gate to source voltage, to attract the holes into the channel region. So how do you get the negative VGS? Because you're connecting your source to the VDD, or the highest voltage in the circuit. You're connecting the source to the highest voltage in the circuit. Any voltage that you apply at the gate, which is less than that highest voltage in the circuit, will give you a negative VGS. Okay? So this is just the dual of your NMOS systems, that in your NMOS system, you ground the source and you apply any positive voltage at the gate, and that gives you a positive VGS. For PMOS, you connect the source terminal to VDD, and then you apply any gate voltage that is less than VDD, and that will give you a negative VGS to create this channel. So just think of it as a dual of your NMOS based systems. So for NMOS, your VGS had to be larger than VT. For PMOS, your VSG has to be larger than the absolute value of the threshold voltage of the MOSFET. Why I am taking the threshold voltage? Because remember, to create a channel, you needed to apply a negative voltage. So the threshold voltage for PMOS is negative. The threshold voltage for NMOS was positive. Because the PMOS is a dual of it, the threshold voltage of the PMOS will be negative. And that's something we can see from this diagram, that unless you apply a negative voltage at the gate, you cannot create the channel. Right? So you have to apply a large enough negative voltage to make sure that it crosses the threshold of creating the channel. So the way you should represent the condition for the MOSFET to be on for a PMOS is that you take VSG, and that has to be greater than the threshold voltage. So this looks very similar to the NMOS equation. So the one written on top is the NMOS equation, and the one written in bottom is basically the equation for your PMOS. That the PMOS device will be on when VSG is higher than the absolute value of the threshold voltage. Okay, so what would be your V overdrive? The overdrive voltage will again be by how much amount your VSG is higher than the absolute value of the threshold voltage. So V overdrive will be the absolute value of absolute VGS minus absolute value of the threshold, or just the absolute value of your VSG minus VT. Okay. So you can represent everything with absolute values, and that will make your life much easier. So for NMOS, your equation was that V overdrive was VGS minus VT. Here, if you just represent it with the absolute values, it will stay in the same equation, but your life will be much easier. All right. And also now for the equation for saturation, again the absolute value of your VDS needs to be larger than your V overdrive. That's the equation that you need to satisfy to make sure that the PMOS device is in saturation. Now this will be clear if you just look at one or two examples. So for example, let's take a look at this particular circuit that this was an NMOS, right? So yeah, so let's not look into that. This is just an example of what you have learned before, and this is just an NMOS based implementation. But a PMOS based implementation is over here. So you have a 5 volt that is connected to the source of the PMOS. So 5 volt goes to the source of the PMOS. You are connecting a 1 volt voltage source between this terminal and the gate terminal of the PMOS. What does that mean? What would be the voltage at the gate terminal of the PMOS? If this is 5 volt, if this point is 5 volt, and this voltage source is 1 volt, this point will be 4 volts, right? That's just putting two voltage sources, like considering this path in series, that you'll get 4 volt over here. And in that case, your VG will be equal to 4 volt. Your source, so let's write that down. VG is equal to 4. Vs is equal to 5 volts. So the absolute value of VGS will be equal to 1 volt. Now, whether that is greater than the absolute value of threshold voltage, that will determine whether the transistor is on or not. What is your threshold voltage? Threshold voltage is minus 0.7. Remember that for PMOS, the threshold voltage will be negative. Now, this condition is true, right? Your absolute value of VGS is 1 volt, whereas the absolute value of VT is 0.7, which means that the PMOS transistor will be on. Now, whether it will be active or not, that will depend on whether your VDS, absolute value of VDS, is greater than V overdrive or not. So for that, let's first find out what is your V overdrive. You can already find it out because VGS, absolute VGS is 1 volt, absolute value of VT is 0.7 volt, That means the overdrive voltage is 0.3 volts. Right? And your drain to source voltage, what is your drain to source voltage in this case? If your drain to source voltage, basically the voltage between these two terminals, if your drain to source voltage is more than your overdrive, then your transistor will be in saturation. So if VDS is greater than V overdrive, or absolute value of VDS is greater than V overdrive, you can also write it as VSD greater than V overdrive, because you know that the source is at a higher potential and the drain is at a lower potential. So instead of writing VDS, you can either write it as absolute value of VDS, or you can write it as VSD, because the voltage polarities, or the voltage at which point is higher in terms of source and drain, that just gets reversed for a PMOS. And then you can find out the equation for which your transistor will be in the saturation region. So as you see that the PMOS is very, very similar to your NMOS, it's just that during your analysis, you either have to consider the absolute values, and probably that's the easiest thing to do, that you use the same equation as your NMOS, just consider the absolute values all the time. Okay. The other thing that we want to discuss quickly is something called a current meter. Now, this circuit is basically called a current meter, and we'll tell you why. So, in many of your systems, you'll see that you need to apply an external current. And why do you need to apply an external current? To make sure that your transistor-based circuits are in saturation, or are biased correctly. So you can bias transistor-based circuits using voltage, or you can bias them using current. Now, the problem of biasing transistors using voltage is that voltages are noisy, because there is a lot of noise in any voltage that you can probe in a circuit. So if I looked into voltages in a circuit using an oscilloscope, you might have seen that there is a lot of noise in any point. So voltages are noisy. It can pick up more amount of noise depending on what is the resistance at that point. If the resistance is high, it can pick up more and more environmental noise. So that's one issue with voltages. The other issue with voltages is that there is always a IR drop. Right? So there is something called IR drop in any kind of circuit. So let's say you have let's say you want to bias the gate of a NMOS transistor using a voltage, and that voltage comes from a long distance. So for example, let's say you are creating a custom chip. So if you are creating a custom chip, you'll have a transistor which is somewhere inside the chip, and the transistor has a dimension of micrometers. Right? Usually they have a dimension of micrometers or even nanometers. And the voltage source that you apply from your, let's say, a Keithley voltage source in the lab, that is at a large distance. That is probably at a meter distance from the actual transistor. So the voltage source, the distance between the voltage source, so let's just have a DC voltage source over here. The distance between the voltage source and the gate of the transistor is about a meter, whereas the dimension of the transistor itself is, let's say, a micrometer. So you can just imagine the scale at which the voltages go through. So for example, from here to this point. Now at every point, there will be some amount of leakage. Maybe for biasing, you have created, let's say, let me do this. So let's say you have a resistor to ground over here, and what would that mean is that there would be a small amount of current flow through this resistance. This could be some amount of leakage resistance as well. Even the transistor gate of the transistor has some kind of leakage resistance. What would that mean is that there would be a current flow, even though we say that there is no current going into the gate of the transistor. There would be some amount of current going into these leakage paths, which are present all throughout the wire that you connect with the gate of the transistor. So there would be a current flow over here, there would be a current flow over here, there would be a current flow through this resistor as well. And then there would be series resistances, because you're connecting a wire always has finite resistance. It's never zero resistance, right? Any wire in your electrical system has some finite resistance, right? So there are always these resistances, and that resistances will have some amount of voltage drop. So this resistance will have some voltage drop, this will have some voltage drop, this will also have some voltage drop, and so on. So if you are applying a 1 volt over here, and there is a voltage drop of let's say 10 millivolt here, maybe 50 millivolt here, and maybe another 50 millivolt here. So the voltage that you actually see at the gate of the transistor is 890 millivolt, right? You do not see the entire full voltage at the gate of the transistor. So biasing the transistor using voltages is probably not a very good idea. Generally, what people do is that you try to bias them using currents. And this is one way to bias using a current. Okay. So how you do this is that you have an external current source. Instead of having an external voltage source, you can have an external current source. You connect that external current source through a MOSFET like this. So this is an N-channel MOSFET, and the current goes from the drain to the source. Okay. And let's say you have connected the gate and the drain together using this fashion. So we'll show what this circuit does is that whatever current is flowing into this branch will be same as the current that flows through this branch if the sizes of the M1 and M2 transistors are equal. If the M1 transistor has the same W over L or the aspect ratio as the M2 transistor, then the currents through these two transistors will be equal. The other thing is that as this current is flowing through the transistors, this transistor will develop some amount of VGS, because as you know, for the MOSFET, if the MOSFET is in saturation, the current equation for current is equal to K over 2 times VGS minus VT whole square. Now, depending on how much current you are putting through the transistor, it will develop its own VGS, because that equation has to satisfy anyway. Whether you are applying a voltage at the gate or you are applying a current at the drain, the equation still remains same. It does not change. The equation is your current is equal to K over 2 times VGS minus VT whole square. Now, what I'm saying now is that you can apply a VGS at the gate of the transistor and find out what is the current flowing through it, or you can apply a current at the drain of the transistor, and the transistor will create its own VGS that is required for the same amount of current to flow through the transistor. Right? The transistor instinctively will create its own VGS as you are applying a current at its drain, because this equation has to satisfy anyway. If this is your provided quantity, then this is something that the transistor will create instinctively. If this is the provided quantity, then the current is something that the transistor will create instinctively. So what that means is that you do create a VGS at the gate of this transistor, and that same gate is connected, or the same voltage is connected to the gate of the other transistor. So as you see, this is same as providing that VGS from this external source. But what is the advantage that you get here? That you have a current instead of a voltage, and that voltage is created locally very close to the transistor. So for example, these two transistors can be very close together, which means that the voltage at the gate of this transistor will be same as the voltage at the gate of this transistor. There would be not much effect of noise or IR drop or any other non-ideality. And if you're creating like this voltage with a current, according to KCL, that same amount of current has to flow through the drain as well as the source of this transistor. And if the current does not have much noise, then the voltage that will be created at the gate of the transistor will also not have much noise. So you can also create a very good current source externally and feed that current so that the effect of noise is less when you're biasing the transistor, and also the effect of IR drop is not present at all, because now you do not have these resistances in the path, or even if you have resistances in the path, let's say for example, this current source is, so you're providing a current source from external world, right? So there are resistances in the path, but those resistances do not matter. There would be IR drop across those resistances, but what you are concerned about is just the current flowing through the transistor. You do not even care about the voltages anymore. So that's the advantage of biasing using current sources. Question? Yes, it does not get rid of the noise, the loss along the path. It does not. But you don't care about the loss along the path anymore. Why I'm saying that is that here you apply a voltage and you have a loss along the path. So at this point, you do not see the same voltage. But think about current. There is resistances in the path. There are losses in those resistances. But does your current change along the path? No, right? So if you are applying a 1 ampere, 1 milliampere current here, you'll see the same 1 milliampere current going through the transistor, even if there is voltage losses over it. So all you care about is the current. So this is the difference between current mode analysis and voltage mode analysis. Because of your KCL, the current flowing through the transistor will be same as this current. But because of KVL, the voltage at this point, the gate of the transistor will not be same as the voltage that you apply externally. Question? You will have no the leakage. There is leakage path. So you're talking on the left hand side figure, right? So the leakage is not to ground, right? In this case, so where are the paths where there could be leakage? So from this point, there could be a leakage path to ground because these are physical devices, right? But from this point, there cannot be a leakage path to ground. Your wire does not leak to ground. The gate of the transistor can leak to ground, but not the wire. All right. So now, assuming all of that is true, and we understand the motivation of why we want to use a current-based biasing, now we'll learn how you can use this circuit to sort of create the biasing required for your transistors. Because eventually what you're trying to do is that you're trying to make both of these transistors in saturation. And for example, let's say this is the transistor in your common source configuration. We haven't drawn it that way, but this could be one of the transistors in your common source configuration. And what you're trying to do is just to create a correct biasing for this particular transistor. Now, how to do that? Assuming that this M1 and M2 transistors are matched, what does matching mean? Matching means that they have the same aspect ratios. Now, assuming that they are identical, having the same aspect ratios, and also they have the same parameters. So, for example, the threshold voltages of the two transistors are equal. The K1 dash, that is mu times COX for the two transistors are equal. Let's call it VT, the same threshold voltage that these two transistors have, and K dash is the device transconductance or the process transconductance that both of these transistors have right now. So your M1 transistor is diode connected. The gate and drain are connected together. We have already talked about diode connected transistors in the past. And you have seen that if the gate and drain are tied together, this is automatically in the active or saturation region. Why? Because what's the equation for your active region? Your VDS has to be more than VGS minus VT. Now, if your gate and drain are tied together, the drain voltage will be equal to the gate voltage. So VDS will be equal to VGS. If VDS is equal to VGS, VDS is always higher than VGS minus VT. That's why for a diode connected transistor, you are always into saturation region. Okay. Now, VGS2 is basically the gate to source voltage of the M2 transistor, the second transistor. VGS2 is this voltage, and VGS2 will be equal to VGS1 because gates are connected together and both the sources are grounded. So VGS1, if VGS2 equal to VGS1, you can write VGS1 as VT plus V overdrive. Right? That's the definition, that V overdrive is VGS minus VT, or VGS is equal to VT plus V overdrive. Now, you can write V overdrive as square root of twice I over K. That's something you have used in your homework 4 and homework 5. That's the equation that you get from the equation for saturation. So this becomes VT plus square root of twice I over K, or twice I1 over K1, because you are now talking about the M1 transistor. Now, because the FETs are connected together in this way, V overdrive of 2 will be equal to V overdrive of 1, right? Because gate of the M2 transistor is same as the gate of the M1 transistor. Source of the M2 transistor is same as the M1 transistor. And we have already assumed that the threshold voltages of the two transistors are equal, which means VGS minus VT of both the transistors are equal. Now, if you assume that the M2 is in the active region, let's just assume that M2 is in the active region, which means that VDS2 for M2 is higher than the V overdrive 2, then you can write the current through M2, that is I2, is equal to K2 over 2 V overdrive of 2 squared. Now, because V overdrive of 2 is equal to V overdrive of 1, you can write this as K2 over 2 V overdrive of 1 whole squared. And that is, you can write V overdrive of 1 as square root of twice I1 over K1. Now we can write this as K2 over 2 times twice I1 over K1. And that gives you K2 over K1 times I1. Now what is K2 over K1? K2 is equal to K2 dash times W2 divided by L2. Remember that the device transconductance is equal to process transconductance times the aspect ratio. And K1 is equal to K1 dash times W1 over L1. So if you write that down, that K2 divided by K1, now since we have already assumed that the process transconductances are equal, that is mu times Ux is equal for both the transistors. So K1 dash and K2 dash are equal. But your W over L ratio could be different for the transistors. Or it could be same as well, but let's say for now, let's just assume they are different. So K2 over K1 will become W over L of 2 divided by W over L of 1 times I1. Now you can, if you have L1 and L2 same, the length of the transistors to be same, then the I2 over I1 just becomes a ratio of the widths. I2 over I1 becomes W2 over W1. So that's what we solved for this particular circuit, that I2 over I1 is just the ratio of the widths of the transistors. If the widths are equal, you get the exact same amount of current. That's what we said initially, that if the aspect ratios are same for these two transistors, the currents will be same for I2 and I1. But you can also create any multiplication of the I1 current by making the, let's say if you want I2 to be 2 times that of I1. What you need to do is that you just make width of M2 2 times higher than the width of M1. If you want to create an I2 which is 10 times higher than I1, you just have a M2 which has a width that is 10 times higher than the width of M1. So I2 over I1 just becomes the ratio of W2 over W1. Okay, now how to create these current meters with different ratios of FETs. So what is one way to create these different widths of transistors? You can have the same transistor and put the transistor in parallel with the previous one. So for example, in this case, on the right hand side, you see that 3 transistors are in parallel. What does that mean is that the width of the transistor, the overall transistor becomes 3 times that of the width of the individual transistors when you put transistors in parallel. And again, why is that? That is because if you think about the structure of the transistor, when 3 of these transistors in parallel, what does that have? The gates are all connected together, the drains are all connected together, and the sources are all connected together. Right? So you have 3 parallel paths for the current to flow. So you can actually have 3 times the current if the gate voltage is similar for all the transistors. Right? So there are 3 parallel paths for the current to flow, but the gate voltage of all 3 transistors are same. So you have 3 times the amount of current flowing through the entire system as compared to only 1 transistor. So that is same as saying that the W over L of this transistor assembly is 3 times that of the individual transistor. Because what is current? Current is equal to basically K over 2 times V overdrive squared. And you already know K can be written as K prime times the aspect ratio. So now, if the aspect ratio is 3 times wider or 3 times higher, you get 3 times the amount of current. That's what you're doing over here. The other way of saying is that because the current is 3 times higher than one individual transistor, the aspect ratio has to be 3 times higher. On the other hand, in the left side, you have 2 of these transistors connected in parallel. The gates are connected together, the drains are connected together, and the sources are connected together. So what would be the mirroring ratio in this case? So if this current is I1, this I2 will be 3 over 2 times I1 or 1.5 times I1. So you can also create fractional ratios of currents using this circuit. So for that, you just have to make the number of transistors or the number of unit widths on the two sides a fractional ratio and not an integer ratio. Let's say if you had 2 of them on the left and 4 of them on the right, the ratio will be 4 over 2, that is equal to 2, right? So you can create any ratio. It could be an integer ratio or fractional ratio of transistors by using this current mirror circuit. All right. Now, remember that if you do consider the effect of lambda or the effect of channel length modulation or the effect of VDS, then this does not remain as simple. So this is assuming, so as you see that over here, we consider the equation of current, which does not take into account the effect of lambda or channel length modulation. If you take the effect of channel length modulation into consideration, your I2 over I1 will be W2 over W1 times 1 plus lambda VDS2 divided by 1 plus lambda VDS1. And that again directly comes from these equations. So when you take the lambda or the channel length modulation parameter into consideration, your I2 over I1 will be slightly different from this case where you did not take the channel length modulation into consideration. But it will probably not vary too much, because if you have if your W2 over W1 is something that dominates the amount of current that will be seen in the second branch. Now, what's the application of it? That you can create from one current source, you can create multiple current sources. The advantage in that case is that, let's say, so for example, how are you creating these multiple current sources? Let's just think about it for a moment. So for example, this part of the system is something that we have discussed before, that you have a current source, you have this diode connected M1 transistor, and through the M2 transistor, the current flowing will be a ratio of the aspect ratios of M2 and M1 transistors, right? So that's how we'll find the I2. Now you can mirror this I2 current using the same technique, but with PMOS transistors on top. And in that way, you can create these source currents. So I2 is a source current, which means that this current is sourced into a let's say a load circuit of your choice. This is again a source current, and this is again a source current. So you can create 3 different, or maybe you can keep on creating these current sources by adding more and more PMOS transistors on the right hand side. So what that does is that you can, from one single external current source, you can create multiple internal current sources. And why that could be important? Because remember that you could have multiple amplifiers in your system, or multiple components in your system. You can probably have a filter, you can have an amplifier, you can have a buffer, and so on. And all those different components in your system may require biasing, or in fact will require some kind of biasing. So by creating these many different current sources internally, you can bias each of the components separately, just from one external current source. Questions?
So I2 equal to I4 equal to I5.
That depends on the ratio of the M4, M3, and M5 transistors. Now you can have so M1 and M2, the ratio of M1 and M2 transistors will determine the ratio of I1 and I2. Let's say they are equal, so I1 is equal to I2. But let's say the ratio of M3, M4, and M5, they are 1, 2, and 4. Let's say a binary weighted ratio of M3, M4, and M5 transistors. Now you have a binary weighted current I2, I4, and I5. So current I4 will be 2 times that of I2, current I5 will be 4 times that of I2, and so on. So you can create any different ratios depending on the ratio of the transistor. And you can provide these current sources to, let's say, multiple components of your system. So you eventually have only one single current source externally, but internally you can feed that current to multiple different components, so that you can bias all the different components separately just from one single external source. Question? So if lambda is 0, then it will just be a ratio of these widths of these transistors, assuming the lengths are similar, right? The lambda is not zero. That's a great question. In the real world, the lambda is non-zero. So you'll see that there is some amount of difference. Even though you say that the ratio has to be 1:2:4, you'll probably see the ratio is 1:1.9:3.7, something like that. Yeah, that's true. That's true. So those are non-idealities in the system. But assuming that the non-ideality is not present just for a second, you can create any current, any amount of current from one single current source in the external world. Yeah, so this is one application where this is called current mirroring, that you are mirroring the current, and that mirroring ratio could be 1. The mirroring ratio could be something that is not equal to 1 as well. More questions. The use case, yeah. So as we said that the use of having, so initially what we were discussing is that you want to bias transistors, right? And we said that biasing using voltage is probably not a good idea because of noise, interference, and IR drop. But biasing using currents is a better idea. Now you can have different components. Let's say you have 2 different amplifiers, 4 different filters, 3 different buffers, and you want to bias each one of them separately. So either you needed 7 or 8 different voltages from the external world, or you can have only one current from the external world and mirror that current into 7 different places to create the biasing for all the different components of your system. Okay, so we'll stop here. In the next lecture, I'll be discussing about the MOSFET amplified cheat sheet. So that will give you a everything that we have discussed on MOSFETs on the same place. But I have already shared it on campus. Please go over it if you have time. Otherwise, we'll look at it in the next lecture. Yeah. Let me stop the